So last spring, imagine you go through your whole lecture because you have to do these things when everyone's on, and you go through a 20-minute lecture and you realize that it wasn't recording the whole time.
No.
Yeah. Or you realize, oh, what? The computer actually ran out of hard drive space, right? That happens also sometimes. Let's see, this is a lot of memory. I want to finish off just one example of hypergeometric. We've seen a number of examples. You can go back over the last 4 weeks and you can figure out, oh yeah, when we did that problem, it was a hypergeometric geometric random variable. When we did that problem, it was a binomial random variable, even if we didn't call it. Oh yeah, that one was a negative binomial random variable, so on and so forth. But there was one example that I almost went through. I think I started talking about it in at the time. It was this capture-recapture question. And I just want to talk a little bit about it because it uses something called maximum likelihood estimators, which will be bigger as the semester goes on. And it's sort of an interesting question. It's really a stats question, but we're using probability to answer it. And so in this situation, so this was page 13, and it was example I. Okay, and of course it wasn't called a hypergeometric random variable back then, but that's what it is. It's a hypergeometric random variable. So in this situation, we're trying to figure out, there's this wildlife population out there. Okay. And so here's sort of the setup for the experiment. That someone goes out and they capture 10 animals and they tag them and then they release them. Okay. So we tag 10 animals and then release them back into the wild. Okay. And then of course you allow them, you have your 10 here and then you have your other ones that were already there. And then you allow them enough time to sort of spread out and mix and match. You're hoping things are mixed up again. And then you go out and you capture another, here, and release here. Another 20 animals. And when you capture another 20 animals, you notice that 4 are tagged, right, of those 20. And so now the question is, how large is the population? Now obviously, we don't know and we won't know. Right? Unless we actually go out there into this area and individually count every single one of the animals that are there, we won't know exactly how large the population is. Okay? But there are certain things that we could figure out. Right? So for instance, I know that there are 10 animals that are tagged out there. I know I also found another 16 that were not tagged. So at the very least, I know that there are at least 26 animals out there, right? But, I mean, because I know there, wait, let me make sure I have that right. Yeah, because I did not catch 6 of the tagged animals, right? But I caught 20 animals, so there were at the very least an additional 6 tagged animals out there. But that's assuming the only ones I didn't catch were tagged animals. Okay. And it's probably somewhat likely that I caught some untagged animals out of that, right? So on and so forth. Okay. So I'll never know this answer exactly without going out there and counting everyone, right? I don't know the result of election day until I actually have election day, right? There's certain things I just won't know unless I can check every individual thing. That's where statistics come, right? I can say, well, what's the most likely outcome for the population in a case like this? Okay. So first of all, let's just see this as a hypergeometric random variable, right? Because I'm out there, right, and X will be the number of tagged animals captured. Right. if I think about X is the number of tagged animals captured, I think about this and I have some animals out there. N is the total number of animals. Okay. I'll have, what letter were we using here? M, N, K, let's see. Be a little more careful with my hypergeometric. The good things were R, right? Yeah. R, right, which are the successes, would be my tagged animals. And that's 10. I know that, because I tagged them. Okay. The N minus R, right, which would be my N minus 10, would be the untagged animals. That I would get out of that. Let's see. Here's my sheet for this one. There we go. My untagged animals. Okay. And then M or K or whatever. K is the number collected. And that's equal to 20. Right? So if I think about this, I have this population out there, and I have R equal to 10, I'm just going to put T for tagged animals, and then I have these other animals out there that are not tagged. The problem is I don't know how many aren't tagged out there. Right? I have these N minus 10 that are, I'll put a U there, for untagged. And I'm going to go out there and I'm going to collect 20 at random from that population. Okay? And so I could think about it in this way. There's N animals out there, and I'm going to choose 20 of them. There are 10 from this good group, and I chose 4 of them in this particular case. And there were, there were N minus 10, the total number minus those 10 tagged out there. And how many did I select of that group? 16. Right? And that would be the probability X is equal to 4 for my hypergeometric random variable. So this would be like, what is the probability X is equal to 4? Because I know the outcome of this. I captured 4 tagged animals. So this is my bad / untagged group, and that's my good / tagged group. Okay. So it is. I have these two groups. I have the 10 tagged and the N minus 10 untagged. Right? I'm going to choose 4 from this one, 16. I did choose 4 from this one, 16 from that one. Of course, the total size of the sample space is N. And I chose 20, right? That would be the equally likely sample space in all of that, okay? X is a hypergeometric random variable, and this would be the case if I knew what N was, I would be calculating what's the probability X is equal to 4, what's the probability mass function at the point 4. Now, this is a little bit different because I don't know what N is, right? And I try to figure out, well, what's likely, what is it likely for N to be? Okay. And so, if I want to think about this a different way, it is a hypergeometric random variable, but I could call this L sub N. And this is the likelihood, right? The likelihood of a certain value for N. Okay. So I do think in this class we went through the specific example where N was equal to 40. I think if you go back in your notes back to the second week of classes, I think we calculated this thing for a particular value of N. Okay. But if I think about it, if this would tell me a probability if N is equal to a certain amount, and I would call that a likelihood function for N. And so really this question about, what is the most likely thing is sort of how large, or what's going to give me the largest L sub N, right? Which, state it a little more clearly, which n gives me the largest L sub n. Certain n's will give me certain values, and other n's will give me other values. Let me just give you a picture of this. So if I were to, go ahead and look at the, let's see, is this the one that I wanted? No, the capture recapture down here. Okay. Let's go to this one. Okay, so I'm creating this little vector here that starts at 20 and goes off to 100 for different values for n. Although I could have started at 26, I guess, right? And my likelihood function will be exactly this. I have my n minus 10 choose 16 times my 10 choose 4. I just have those two spots. Divided by my n choose 20 here. And so I could look at that likelihood function, right? And I get all these different probabilities. Each of those is giving me a probability if n is of this thing occurring, if n is a particular value. And if I plot it, I get a plot that looks something like that, right? Which is what, right? It's telling me if my n is a certain value, right? It's telling me how likely is the thing that I saw occur, that is, we collected 4 tagged animals, to happen, right? If there were only 20 or 26 or 28 or even up to about 30 animals, it's very unlikely that I would have only caught that few animals, 4. Now, of course, if there's hundreds of animals, right, it becomes less likely also because I wouldn't expect to get as many as 4. But somehow there's this ideal n, it looks like, or at least a range up here, where if the thing that occurred really happened, to make it most likely, right, it would give me the largest probability, or the largest probability that the thing that I see occurred, right? So we're looking at a picture, a graph of this likelihood function, and we're going to try to figure out which n is going to make it largest. Okay? And the n that makes it largest is how large I think the population is going to be. Now, we don't know. I mean, we can definitely see there's a range in here of things that all seem fairly equivalent. Right? So we'll never know, that just goes along with, we'll never know exactly, but we can at least get, a best answer, and we potentially could get a range of best answers if we really wanted to. Right. So how would we do that? How would we find that maximum value there, where there's a lot of different ways we could do that? Well, there's really only one for this particular example. That is, if I want to figure out which n is going to make this larger, I could do something like figure out when is Ln plus 1 greater than or equal to Ln, right? For which values n is this going to be true? Right? That means that I'd be figuring out where those values are increasing. Right? If this is true, for which n is this true, right? Because that's when I'm on my upward, right? And then after that n, they would start going down. Okay. I'd really be asking, when is the likelihood, right, when it takes a maximum value, right, this is for Maas theorem from calculus, where the derivative function is equal to 0, right, where things really aren't changing much. That's where I find my local maximums and local minimums. Okay. Which in this particular case could be phrased this way: when is L of n plus 1 divided by L of n positive? And then I could go about simplifying, right? Because I have these combinations in here that are pretty messy, right? There'd be this question of, okay, when is 10 choose 4, n plus 1 minus 10, I guess n choose n plus 9, choose 16, divided by n plus 1 choose 20, divided by 10 choose 4, n minus 10 choose 16, divided by n choose 20, right? So here's my L of n plus 1, here's my L of n. I have these two terms, and I want to know where that's greater than or equal to 1. Because that's, as n is greater than or equal to 1, that's where it's increasing. And then I start simplifying. Oh, those two things are the same. I can simplify that, right? And I know I'm not going to go through this. You can go back to page, what did I say, 13, 14. They work through this. But you can see, this is what? This is n plus 9 times n plus 8 times n plus 7 times n plus 6, right? And then I have this 16 factorial and this, right? I have all these factorials in there. And the nice thing about ratios of factorials is if I'm sort of clever enough, I can figure out how to cancel things out. I will give you the punchline and say that when all is said and done with this, not only do those two things cancel out, okay, but I can simplify that to something, I don't have a minute, it looks like, let's see, up there, right? I can simplify it to n minus 10 over n minus 26 times n minus 20 over n. And there would be a question mark here, because I haven't gone back through and double checked this in 3 weeks. I think I had it all right. But essentially, a lot of things are going to end up canceling out with all of this. And when things cancel out, the idea is this is what I would, this is what I get. So I can move these up to the numerator on the other side. I get this quadratic expression that actually has an n squared on both sides, which will cancel out, and it'll get me down to this linear expression, if I have it correct, negative 30n plus 200 is greater than or equal to negative 26n. Right? Which would say 200 is less than or equal to 4n. N is less than or equal to 50. Okay. Right. Again, we're taking these factorials, right? Once we write our combinations as factorials, and we're trying to simplify, and that is the nice thing about factorials is, because we're just multiplying numbers up to a certain point, we oftentimes can cancel things out. And this simplifies so far because the differences here and here are only differing by 1. So a lot of things end up canceling out there. So that's saying as long as n is less than or equal to 50, then the next likelihood function is at least as large or larger than the previous one. Right? And that's what we see if we go back to our graph here. Right? That's what it's showing us here, is that up to about here, which is 50, 50 would be about right here, right? That's my likelihood. In fact, I would get equality at 50, which would tell me that when n is 50, it's equal to the next function out of that. Okay. And if we look here, I guess 50 and 49 are actually equal to each other, if I remember in this case. And if we look in the middle here somewhere, I can figure out where the maximum value here is, and the maximum occurs at 49, well actually 49, 50 are equal to each other, are the same. Okay. And I could probably find that somewhere in here. What's the highest value here? 26, 27, 28, 28.005, 86031, right? So those two right there, which are 49 and 50, give me my largest values. But if I wanted to, I could solve it analytically. I could solve for the n, and I could see, well, n is going to happen at 50, actually, at 49 and 50 here. Okay. So there's an example. That's a question that we'll have where, notice what we had is we have a hypergeometric random variable. Okay. X is I call it Hypegeo, right? Hypegeo has how many parameters?
3.
3, yeah, 3. It has an n. It has a list of good things, 10. And then there are n minus 10 bad things. I don't have to list that because I know what it is once I know what n and 10 are. And then it has the number of things collected, which is 20. But I know I have a hypergeometric random variable, but I don't know one of the parameters. And here I'm trying to figure out what parameter makes sense for the thing that occurred. And that leads us into these likelihood functions and something called the maximum likelihood estimator. About Thanksgiving, we're going to come back to maximum likelihood estimator. But again, this is this is a probability question because we're calculating probabilities. This is a stats question because I don't know exactly what situation I find myself in, and now I'm trying to estimate a parameter, right, given the information that I have, using probability in the thing that's most likely to occur, given that we're working in probability, to make it happen. Okay? So my best guess for the number of animals out there, 50, right? But I could look at my graph and I could see, 50 isn't that much better than 51 or 52, maybe all the way up to 60, right? In fact, I do realize that it could be 80 or 100 out there. It's just a little less likely to be that, right? I would have seen something probably a little bit different if I thought it was going to be that high. Of course, it could be down around 20, 25, 30, but again, what I expect it to be is what I end up seeing, and so I'd probably pick, if I had to pick a range, somewhere between 40 and 60 as an actual range. Right? So again, how do I use probability to answer a question about statistics, right? How do I use, how do I compute likelihoods or use likelihoods to try to figure out what's happening in the world when I don't know exactly what's happening in the world? Here's an example of such a thing. Okay. So anyway, interesting question. It actually leads us into this maximum likelihood estimators. We will get there, again, back around Thanksgiving, but I thought it was a worthwhile question in Hypergeometric. Yes?
So we don't have to go into this, but if we were to do another experiment, we collected, say, another, 15 animals or something, how would that change this? And we don't have to go into this if this is like a different...
So if you release those 20 and then you go back out, you do it again?
Yeah, but if you have multiple experiments to try and really zone in on...
So then the probability, your functions would change, and then you'd have to figure out how to go about doing that. Because now what would we do? We'd have to figure out a way of saying, okay, what would my likelihood function look like now, knowing that I ran this experiment twice. The first time I ran it, I got a 4, right? And then the second time I ran it, I got something. So we'd have to set up new likelihood functions. Okay. There is something that's worth noting here, right? Is that the answer that it gives. So, and the book points this out, and your question reminded me of this. What is the expected value for a hypergeometric? I told you didn't have to memorize it, but does anyone remember it off the top of their heads? It looks, if nothing, just remember it looks an awful lot like the NP of the binomial random variable, even though it's different than the binomial random variable. And the N is the number of things I would collect, which would be my 20. Okay, and the P would be the ratio between the number of good things, which are 10, or the successful things, and the total number of things, which would be our N. And notice, if I take 20 times 10 over N, if that's what I expect to happen, and what happened was 4, and I solve for this, okay, I'm going to get N equals 50. Okay. Multiply both sides by N, divide both sides by 4. 20 divided by 4 is 5, times 10 is 50. Okay. So, what I expected to occur actually gave me the most likely thing to occur. Right? This is a certain type of parameter estimation, right? Or think about it this way, the number of sort of successful things to the total number of things would be in the total population. I'm estimating to be in my sample, the number of successful things to the total things I collected in the population, right? And so it gave me that same N. So one thing is, if we did this again, we could update what our expected value was, right? If we got 5 the next time, then maybe we'd say, well, okay, so my expected value seems to be 4.5, right? If I average those two things that occurred, and maybe now that, I would use it in a similar way to that. Okay. But again, what we expect to happen is sort of what we're expecting to happen, right? So our expected value means a lot of things, but if my expected value is, if what happened is 4, I'm making this underlying assumption that it is, at least in this case, it is very likely that that 4 is supposed to be my expected value, and then which n would give me that, and the answer is n equal to 20. Now, it could be we had a freak experiment, right? We could have had it, there could be 20, there could be 30 things out there, right? And we just happened to get fewer than we were expecting to get if that were true, right? Your predictions are only as good as your data. And so, you know, if you go out there and something that is unexpected happens, right, because it's not really what the situation would warrant, you know, I can still flip a coin 100 times and get 100 heads in a row. It's just not very likely to happen, right? So again, your predictions are only as good as your data, and if we did a poor job, right, if we released all 10 of those things here, and we walked away for 10 minutes and we came back and caught the first 20 things, that might not be a good experiment because there was certainly not enough time for these things to mix again. All right. Okay, so that's our hypergeometric. I will, if you have more questions, we'll be pretty much be done with discrete random variables today with material. We can spend a good bit of time on Friday talking a little bit about some follow-up questions, especially with hypergeometric if you want. But I do want to introduce Poisson random variables. In the grand scheme of things, Poisson random variables come up more often. I guess I would say they're a little more valuable than than some others, right? They come up and they're useful in their own way. Okay. Let's see. Okay, so Poisson random variables. One parameter, I'm going to call it lambda. Let me give you the probability mass function. Let me give you the expected value. I'll give you the variance. We'll do some examples, and then we'll go back and try to understand why it's doing what we claim it's doing. So if x is, I guess I'll use this, Poisson with parameter lambda. So if it's a Poisson random variable with parameter lambda, the probability mass function, piece of k, the probability x equals k will be equal to e to the negative lambda, lambda to the k over k factorial. And that's for k equals 0, 1, 2. This is the one that's tied in with the Taylor series for an exponential function. If you remember back to Calc 2, e to the x is equal to the sum k equals 0 to infinity of x to the k over k factorial. Okay. So I know if I sum up the probability mass function, it should sum to 1. Right. So if I sum up e to the negative lambda, lambda to the k, e to the negative lambda, times lambda to the k over k factorial, right. I'm summing this over the k's, I can pull out the e to the negative lambda, and then I'm just summing up these things that look like lambda to the k over k factorial, and I know from my Taylor series back in Calc 2, that this thing here should just sum to e to the lambda. And e to the negative lambda times e to the lambda is equal to 1. So what did we learn from all of this? I guess right now we learned, we could take any Taylor series which had positive coefficients attached to it, right? Because we don't allow for negative probabilities. With positive coefficients that range from 0 to 1, and I could turn it into a probability, I could turn it into a random variable, I could turn it into a probability mass function. But there is a reason why this one is valuable, and maybe another one isn't. Okay. So there's my probability mass function. Let me give you the expected value, lambda. And let me give you the variance. lambda. That's an easy one to remember. And again, I put up on Blackboard, maybe we'll come back and compute some expected values, but essentially it's similar types of things to what we did with the binomial theorem and the binomial random variable, the geometric series, and the geometric random variable, where we're manipulating things we ultimately want to add up. Not something that looks like this, but what happens if there's an extra k sitting in front of there and we sum it up, right? And my claim is that if we do that, it's going to sum to lambda, right? And then we probably calculate the second moment, so we want to, what's going to happen with a k squared. So there's a worksheet, or there's a handout on Blackboard you can go back and look at that calculation. Maybe we'll come back to it, it just sort of depends. But I want to, this is a useful random variable, and so I want to make sure that we understand where we're going to use it. Okay. Then we'll come back and see why it's related to the binomial random variable. Okay. All right. Okay. So what sort of examples, what sort of situations would we end up using this? So here's an example. Here's some examples of things that will be Poisson random variables. Okay. So if we're waiting for something, or if we want to count how many times something happens in a given amount of time, it actually turns out Poisson random variables sort of fit into that category. So here's a question. So suppose there's this switchboard, right? This place that collects phone calls, takes in phone calls, right? And this office, right, collects phone calls. Let's say they receive, on average, lambda equal to, well, let's say, 5 calls per hour. And let's say I have a question like, what is the probability they receive no calls in the next, well, let's just do it, in the next hour. My claim is, this is X, a Poisson random variable with parameter lambda equal to 5. And then the answer would be, right, what's the probability they receive no calls would be, what's P of 0, okay, which would be my e to the negative 5 times 5 to the power of 0 over 0 factorial. And 0 factorial is what? 1. 1. By definition, it's 1. Okay. And so the answer would be e to the negative 5, which is a fairly small number. Where's the e on this thing? E. It's dust. I don't even see an e on this thing. Table one, I'll have the e somewhere. Or will it? Maybe it's not that important. Oh, there it is. There we go. So, e to the negative 5, pretty small number here. This is 0.00674. Less than 1%. Okay. You know, and if I want to know what's the probability they receive at least 5, right? Then I would want to know. Okay, I want to sum up my k's starting with 5, right? So the probability that x is greater than or equal to 5 would be I'd sum from 5 off to infinity, because this thing can go on forever, and I would solve things that look like e to the negative 5, 5 to the k over k factorial. And probably I'd just say, okay, it's going to be 1 minus the probability x is less, that we get at most 4. Okay, right? But we could do that sort of thing. So I claim those types of questions are Poisson random variables. Okay. And then also the other nice thing is the Poisson random variable is very scalable. Did I spell that right? Scalable, right? We can rescale it, right? Meaning that if my question is, here's a better question. What is the probability. So I know that we receive on average 5 calls per hour. What is the probability that they receive no calls in the next 15 minutes? Then I'll claim this is also a Poisson random variable, but probably not with lambda equal to 5, because 5 indicated that over the next hour we expect to have, that's the expected value, 5 calls. If I expect to have 5 calls over the next hour, how many calls do I expect over the next 15 minutes?
1.25?
1.25, right? 5/4, right? Because I'll divide the hour into, right? Which is 1.25. Okay. So my claim is then, if I want to switch it, if it was 20 minutes, then it would be 5/3. If I want to know what's the probability something happens over the next 2 hours, my lambda would be 10, because I would expect 10 calls over the next hour. That's what I mean by it's scalable. If I have this question, if I kept track of something over a certain time period, and now I want to check it over a different time period, my lambda just changes accordingly. Okay? So now no calls over the next 15 minutes would be the probability x equal to 0 for this new Poisson random variable, which would be something like an e to the negative 5/4, 5/4 to the 0 over 0 factorial. And in this case, it would be 0.286. A little bit more likely that in the next 15 minutes. So if somebody needed to step out, and they weren't manning these phones for 15 minutes, well, there was almost a 30%, there's a 29% chance that that nobody would have called over that time period, which then means that there's over a 70% chance that somebody would have called, at least one person, maybe 2, maybe 3, maybe we could have had 5, we could ask what's the probability there'd be 5 people. Right. So if I know something like this, Poisson random variables are nice in that they allow us to rescale. Right? If the same question was, or in the same setup, what's the probability that I get at least 1 over the next 15 minutes, then the answer would be 1 minus that, right? It would be 1 minus the probability x equal to 0, the complement of it. 1 minus 0.286 approximately, so that would be a 0.714 or something like that. Okay. Right. So other types of things. What else is a Poisson random variable? So what if I have, and if I wanted to switch that to half hour and ask questions, I certainly could do that also. Here's another question. Suppose a region averages, let's see, 1 earthquake every 2 months. Maybe 1 earthquake over a certain minimum level every 2 months. What is the probability of no earthquake in the next 6 months? Something happens every 2 months. I mean, it could be that we have several of these 2 months in a row that this sort of thing doesn't happen. So, initially, right, this I could think of as a random variable, right, a Poisson random variable. If my scale is every 2 months, it would be once every 2 months. If my scale is 6 months, how many did I expect over 6 months? Well, if I expect 1 every 2 months, how many do I expect every 6 months? 3. So I could think about this question, if my scale is on the 6-month scale, is a Poisson random variable with lambda. And then it's just this question, what's the probability x, I'm just thinking probability x equal to 0 because I don't have as many things to calculate. But we could do any probabilities we wanted to. What's the probability there's at most 3 in the next 6 months or something like that? We can certainly do that. And the answer would be e to the negative 3, 3 to the 0 over 0 factorial, right? E to the negative 3, which is approximately 0.05. Okay. About a 5% chance, right? Given that they occur on average of 1 every 2 months, the probability that we'd have none in the next 3 months, or 6 months, right, 3 time periods, turns out to be 5%. Okay. What is the probability that we have fewer than 3? I just compute the probability that there is 0, the probability there's 1, the probability there's 2, the probability there's 3, and I would add those 3 things together. I'm not going to do that in front of you right now, but we can certainly just do that. Okay. Or, just to make a little plug for it, if I had the cumulative distribution function, I would just plug 3 into my cumulative distribution function because that is the function, capital F of 3, which would tell me the probability x is less or equal to 3. Okay. But I sent out a handout yesterday that gave us the cumulative distribution function for the geometric random variable. That is the only random variable we have a nice form for a cumulative distribution function, right? And when we do, it's nice because if I want to take a probability over an interval instead of at an individual point, it's much nicer to have a function that's set up to handle an interval. It's just that with our discrete random variables, for the most part, we do not have nice functions, right? When I do a partial sum of this up to some value n, there is not a nice formula. I know if I go off to infinity, there's a nice formula for that, right? Well, actually, it sums to 1. But if I stop at a certain value n, there's not a nice formula. So far, the geometric random variable is the only one that's given us a reasonably nice formula for that. Okay, so we don't use them very often now, and I would just have to calculate it in each case, and then plug it in. Okay. Okay. So, this is the idea, right? This is a Poisson random variable. Notice, let's see, I guess I'll ask this question. How is this like a binomial random variable? Right? In some way, if I think about an earthquake as a success, what am I doing? I'm really just asking how many successes I'm going to have, or not have in this case, over a certain time, right? So it's sort of like, if this is an experiment that's happening over the next 2 months, and I say, well, on average, I expect one success, but now I'm going to take a new time interval, right? Now I'm going to do 3 of those, and now I'm asking, well, what's the probability of 1 success or no success, right? I would expect 3, but what's the problem? So in some ways, it seems like if I think about a call as being a success, is that sort of thing, how many successes am I going to have over a certain time interval? And so in some ways, it seems very much like a binomial random variable. In fact, it is very much like a binomial random variable, because that's exactly what we're doing. X is counting the number of successes over, but it's a little different, right? Because with a binomial random variable, I was counting the number of successes over a fixed number of Bernoulli trials, right? I say I'm going to run this Bernoulli trial a certain number of times. Now I'm counting the number of successes over a fixed what? At least in all of these cases, time. There's another example, I don't remember if it's in this book or not, but you could also use it if you're typing something. Let's say you average a half of it, 1 error every 2 pages, and so you type up a 10-page paper, and you could ask the question, what's the probability that you end up with a certain number of errors in that 10-page paper, right? So typing errors like that. There, it would be over a fixed sort of distance in some way, but it's the same idea, where you're counting a success would be a typo, and it'd be the number of successes over some fixed, and it would rescale from 2 to 10 and so on and so forth. So it's a fixed time instead of fixed Bernoulli trials. So it's a little different. Trials, not trails. Bernoulli trials. But otherwise, it's sort of the same in spirit. And so how is it different, right? How is it the same? So now what we're going to do is we're going to have, from now out to some time t, right, 3 months or 20 minutes or whatever it's going to be, I have this expected value, I have this average value here. Okay. And the way we're going to look at this problem is we're going to start asking the question, we're going to start breaking this time interval down into smaller and smaller time intervals. I have this big time interval, maybe I have these 20 minutes, and I'm going to break it down, and I know I expect, how many successes did I expect in 20 minutes? Or in 15 minutes? In 15 minutes I expected 1.24 successes. Okay. But now I can take these 15 minutes and I can break them down to 1 minute interval. And each of those I would expect, well, whatever 1.25 divided, 1.25 divided by 15 would be, right? There'd be a certain likelihood of success. But the way I could think about this is, at any moment, or every small time interval, I'm testing to see, is there a success, right? Did I receive a call? Did an earthquake occur, right? Every moment, I'm sort of thinking about this over these small time intervals, and I'm going to let these time intervals shrink farther and farther. So I could end up, I'm going to have a lot of failures, no calls, and then there'll be a call, and then there'll be no calls again for a while, and then a call, and then a no call, maybe another call, right? And so on and so forth. Okay. So if I wanted to think about it as a Bernoulli trial, I just have to figure out, well, what's my p, and then as I take a small time interval, what's the likelihood of success? And so what we're going to do, where the Poisson random variable goes, is if I keep subdividing our time intervals into smaller and smaller time intervals and smaller time intervals, so that instead of every minute, every 10 seconds, every second, I ask whether or not there's a success, but as I'll just say, my delta t approaches 0, right? If I keep asking that, I end up getting this Poisson random variable. Right? So it is the binomial random variable when we let the number of Bernoulli trials go off to infinity, right? But also the probability of a success over a certain time interval goes down towards 0. Right, because it's a shorter Bernoulli trial there, we'll end up with this random variable. Okay. So let me show you. We can at least get it started here. Where's the note here? There it is. We can at least set it up. So remember, a binomial random variable looks like this, right? It has 2 parameters, an n and a p. By the way, what's going to be the relationship between lambda and n and p?
Isn't that the expected value?
It'd just be the expected value. So my lambda will be n times p, right? That's the sort of equivalent there. Okay. Or write it this way, my p would be lambda divided by 10. I can think about it that way. And so my binomial random variable would look like this. The probability x is equal to k is n choose k, p to the k, 1 minus p to the n minus k. And now I'll just go through this calculation. So n choose k would be n factorial over k factorial, n minus k factorial. And then my p to the k, I'm going to think about as lambda over n to the k. And my 1 minus p to the n minus k, I'll think of 1 minus lambda over n to the n minus k. So this is a binomial random variable, and we'll have to stop here because we're at the end of class. I'll pick it up because it won't take very long. It's a worthwhile thing to do, but we're going to ask the question, what happens to this expression right here as n goes off to infinity, right? Because as I take my Bernoulli trials and I allow for more and more Bernoulli trials, but every time I sort of break up my Bernoulli trials into these smaller Bernoulli trials because, you know, I only have half the time, I don't expect the probability of success to stay the same, that the relationship between that and, you know, what we have is lambda over n. As n goes off to infinity, it turns out, I don't have to rewrite it, we're going to get that as the limit. Okay. So as we let our Bernoulli trials go out to infinity, so that, and the probability of a Bernoulli trial go out to 0 in this way, we're going to end up getting this for our probability mass function. And so then we can see, yeah, this is actually just this idea of breaking my time intervals into these smaller and smaller time intervals and asking and counting the successes I come out of it. Okay. All right, so we'll stop there, but we'll do that, and I'll give you some homework on Poisson. But it's a very useful random variable in a lot of situations. Yes? You don't necessarily need to memorize it, but it was this one. I sent out 1 minus p. And that's for x, a geometric random variable with parameter.
Oh, that's the one that
So it's
that makes sense intuitively.
yeah, there's a couple ways of thinking about it because this would be you know, failures, a certain number of failures in a row when you're looking at the complement.
Yeah, that you get all failures.
Yes. So so right now it's the only cumulative distribution function that makes any. We can actually come up with a closed form, reasonably nice function.
Yeah.
Okay. Teach or Lord at hillsdale.edu. So
But the last 3 problems for that hypergeometric handout, it was asking, it set up the scenario, but it was asking, count the number of red balls until the first red ball is drawn, something like that. I was wondering if that was actually.
oh, probably case problem. I'd have to go back and look at the problem, but count the number of draws until the first red ball or second red ball, something like that.
Yeah, I kind of assumed that was what it was, but
Yeah.
I just wanted to.
Okay, that's probably what it was.